Okay, boys and girls, this evening we are looking at the squeeze theorem, also sometimes known as the sandwich theorem. We're going to use the squeeze theorem to solve complicated limits. The squeeze theorem is a pretty nifty little theorem. It basically says this: if you have two functions, h of x and f of x in this case, and one function is greater than the other function. So in this particular instance, f of x is greater than h of x. If that is the case, and there is a third function in between f of x and h of x, as you see here, then if the limit as x approaches some constant of f of x is the same as the limit as x approaches that same constant of h of x, then the limit of g of x as x approaches that constant would be the same. Okay? So if you notice here, visually, you can see f of x is greater than h of x, and the red one is in between them, but at a, all three of them would have the same limit because the limit of f of x is the same as the limit of h of x. So let's do a couple of examples just to see how we could use that. I am going to do A and A, 1A and 2A, and I'm going to let you do 1B and 2B for homework, and we'll talk about it tomorrow. Okay, so in this first example, we see that f of x is in the middle, is sandwiched, is squeezed between h of x and g of x. So we want to find the limit as x approaches c of f of x. In our first example, c is 0. So to do that, we would have to first look at, because h of x is less than g of x, we would have to begin by looking at the limit as x approaches 0 of h of x. And to find this limit, we could just do a direct substitution. And we see that that limit is 4. And then we would have to find the limit of g of x. So the limit as x approaches 0 of g of x, again, doing a direct substitution, we get 4 plus 0 squared is 4. And since the limit as x approaches h of x as we approach 0 is equal to the limit as x approaches 0 of g of x, therefore, the limit as x approaches 0 of f of x, which is in between the two, must also be 0.
Oops, I said 0, but I meant 4.
Okay, now we're going to use the squeeze theorem to prove that the limit as x approaches 0 of this particular function, x squared cosine 20 pi x, is 0. Okay, we could do a direct substitution and prove that, but let's use the squeeze theorem. Okay, so using the squeeze theorem, we're going to start by looking at simply cosine 20 pi x, because I know a thing or two about 20 cosine pi x. So the limit as x approaches 0 of 20 cosine pi x, I know that that has to be bounded between -1 and 1. How do I know that has to be bounded between -1 and 1? Well, the amplitude of cosine is 1, even though I wrote this incorrectly. I wrote that wrong. Cosine 20 pi x, the amplitude is 1, meaning that the highest it's going to go is 1, the lowest it's going to go is -1. Okay, so I know that this limit has to be between -1 and 1. That doesn't help me much because I'm looking for x squared. Well, what if I took the limit as x approaches 0 and I multiplied this quantity by x squared, cosine to 20 pi x? Well, if I multiply cosine 20 pi x by x squared, then to solve this equation, I would have to, this inequality, I'd have to multiply the -1 by x squared and the 1 by x squared. Now, because I've done this, now I can use the squeeze theorem. I know that negative x squared is below x squared. I know that. Of course, if I graph it, I get this and I get that. So I know negative x squared is below x squared. So therefore, this is in the middle of the two. This would be in the middle of the two. So to find this limit, I can say the limit as x approaches 0 of negative x squared is 0. And the limit as x approaches 0 of x squared is 0. And since those limits are the same, I can now say that the limit as x approaches 0 of x squared cosine 20 pi x is also 0. And I have proved that using the squeeze theorem, even though I could have proved it simply by doing a direct substitution. Okay, boys and girls, did you get that? I will see you tomorrow.